Each type of hardware or hardware architecture will support a number of atomic instructions. Some examples include test and set, or read and increment, or compare and swap. Different instructions may be supported on different hardware platforms. Not every architecture has to support every single one of the available atomic instructions out there. As you can tell from the names of these instructions, they all perform some multi-step, multi-cycle operation. But because they're atomic instructions, the hardware makes guarantees that this set of operations that are included in these instructions will happen atomically, so not just halfway, the entire operation or none of it. That it will happen in mutual exclusion, meaning that only one instruction at a time will be allowed to perform the appropriate operation, and that the remaining ones will be queued up, we'll have to wait. So if we think about this, what this means is that the atomic instructions specify some operation, and this operation is the critical section, and the hardware supports all of the synchronization-related mechanisms that are required for that operation. If we look at our spin-lock example using the first atomic test and set operation, the spin-lock implementation can look as follows. Here, test and set automatically returns or tests the original value of the memory location that's passed as parameter, lock in this case, and sets the new value of this memory location to be 1. This happens automatically. Remember, 1 to us indicates that the lock is busy. When we have multiple threads that are contending for this lock when they're trying to execute this spin lock operation, only one needs to successfully acquire the lock. The very first thread that comes to execute the test and set, for that thread, test and set will return 0 because the original value of the lock was 0. Originally, the lock was free. That thread will therefore exit the while loop because test and set will return 0, free, and that is different than busy, 1. That is the only thread that will acquire the lock and proceed with the execution. All of the remaining threads that try to execute test and set, for them, test and set will return 1 because this first thread already set the value of lock to be 1. Therefore, those remaining threads will just continue spinning into this while loop. Notice that in the process, these other threads, they're repeatedly resetting the value of the lock to 1. So as they're spinning through the while loop, every single time they try to execute this test and set operation, this sets the value of the lock field to be 1 again, to be busy. However, that's okay. The very first thread, when it executed test and set, that already set the value of the lock to be busy. And these other threads are not really changing the fact that the lock is indeed locked. Which specific atomic instructions are available on a given platform varies from hardware to hardware. Some operations like test and set are pretty prevalent. Others, like read and increment, may not be available on all platforms. In fact, we may have versions of this where in some cases there is availability of an atomic operation that atomically increments something, but it does not necessarily return the old value. In other cases, there may be atomics that support read and decrement as opposed to read and increment. In addition, there may be differences in the efficiencies with which different atomic operations execute on different architectures. For this reason, software such as synchronization constructs that are built using certain atomic instructions has to be ported. We have to make sure that the implementation actually uses one of the atomic instructions that's available on the target platform. Also, we have to make sure that the implementation of software of these synchronization constructs is optimized so that it uses the most efficient atomics on a target platform and so that it uses them in an efficient way to begin with. Anderson's paper presents several alternatives on how spin locks can be implemented using available hardware atomics, and we will discuss these in the remainder of this lecture.